Today we will discuss what we call uniform circular motion. What is uniform circular motion? An object goes around in a circle, has radius r. When the object is here, this is the velocity. It's a vector, perpendicular, and later in time when the object is here, the velocity has changed, but the speed has not changed. We introduce t, what we call the period, of course it's in seconds, which is the time to go around once. We introduce the frequency f, which we call the frequency, which is the number of rotations per second. And so the units are either second minus 1, as most physicists would call it hertz. And so frequency is 1 divided by t. We also introduce angular velocity, omega, which we call angular velocity. Angular velocity means not how many meters per second, but how many radians per second. So, since there are 2 pi radians in one circumference, in one full circle, and it takes t seconds to go around once, it is immediately obvious that omega equals 2 pi divided by t. This is something that I would like you to remember. Omega equals 2 pi divided by t. 2 pi radians in capital T seconds. The speed, v, is of course the circumference 2 pi r divided by the time to go around once, but since 2 pi divided by t is omega, you can also write for this omega r. And this is also something that I want you to remember. These two things you really want to remember. The speed is not changing, but the velocity vector is changing. Therefore, there must be an acceleration that is non-negotiable. You can derive what that acceleration must be in terms of magnitude and in terms of direction. It's about a 5-6 minutes derivation. You'll find it in your book. I have decided to give you the results so that you read up on the book, so that we can more talk about the physics rather than on the derivation. This acceleration that is necessary to make the change in the velocity vector is always pointing towards the center of the circle. We call it centripetal acceleration. Centripetal, pointing towards the center, and here it's also pointing towards the center. It's a vector. And the magnitude of the centripetal acceleration equals v squared divided by r, which is this v, and therefore it's also omega square r. And so now we have 3 equations, and those are the only 3 you really would like to remember. We can have a simple example. Let's have a vacuum cleaner, which has a rotor inside, which scoops the air out or in, whichever way you look at it. And let's assume that the vacuum cleaner, the scoops, have a radius r of about 10 centimeter, and that it goes around 600 revolutions per minute, 600 RPM. 600 RPM would translate into a frequency f of 10 hertz. So it would translate into a period going around in 1/10 of a second. So omega, angular velocity, which is 2 pi divided by t, is then approximately 63 radians per second. And the speed v equals omega r is then roughly 6.3 meters per second. The centripetal acceleration, and that's really my goal, the centripetal acceleration would be omega square r, or if you prefer, you can take v square over r. You would get the same answer, of course, and you will find that that is about 400 meters per second square. And that is huge. That is 40 times the acceleration due to gravity. It's a phenomenal acceleration, a simple vacuum cleaner. Notice that the acceleration, the centripetal acceleration, is linear in r. Don't think that it is inversely proportional with r. That's a mistake, because v itself is a function of r. If you were sitting here, then your velocity would be lower. Since omega is the same for the entire motion, you really have to look at this equation, and you see that the centripetal acceleration is proportional with r. Therefore, if this were a disk which was rotating, and you were at the center of the disk, the centripetal acceleration would be 0. And as you were to walk out further out, it would increase. Now, the acceleration must be caused by something. There is no such thing as a free lunch. There is something that must be responsible for the change in this velocity. And that something I will call either a pull or I will call it a push. Now, next lecture, when we deal with Newton's laws, we will introduce the word force. Today, we will only deal with the words pull and push. So there must be a pull or a push. Imagine that this is a turntable, and you are sitting here on the turntable, on a chair. It's going around with angular velocity omega, and your distance to the center, let's say, is little r. You're sitting on this chair, and you must experience, that is non-negotiable, centripetal acceleration, A of c, which is omega squared times r. Where do you get it from? Well, if your seat is bolted to the turntable, then you will feel a push in your back. So you're sitting on this thing, you go around, and you will feel that the seat is pushing you in your back. And so you feel a push. And let's give the push, I can give this a red color for now. So you'll feel a push in your back. That push, apparently, is necessary for the acceleration. Alternatively, suppose you had in front of you a stick. You're not sitting on a chair, you don't get a push from your back, but you hold on to this stick, and now you can go around by holding on to the stick. Now the stick is pulling on you in the same direction. So now you would say, aha, someone is pulling on you. Whether it is the pull or whether it is the push, either one of the two is necessary for you to go around in that circle on that turntable with that constant speed. Now the classic question comes up, which we often ask to people who have no scientific background. If you were to go around like this, and something is either pushing on you or is pulling on you to make this possible, suppose you took that push out all of a sudden. The pull is gone. What is now the motion of the person who is sitting on the turntable? And many non-scientists say, well, it will do like this. That's sort of what your intuition says. You go around in a circle, and all of a sudden you no longer have the pull or the push, and you go around in a spiral. And obviously that is not the case. What will happen is, if you have, at this moment in time, a velocity in this direction, and you take the pull or the push out, you will start flying off in that direction. And depending upon whether there is gravity or no gravity, there may be a change, but if there were no gravity, it would just continue to go along that line, and you would not make this crazy spiral motion. I have here a disk, which we will rotate, and at the end, the edge of the disk here, we have a little ball. And the ball is attached to that disk with a string. So now this is vertical, and so this is going to go around with angular velocity omega, and we have a string here, and the string is attached to this ball, and the whole thing is going around, and so at one moment in time, this has a velocity, like so,